All right. So yes, I attended the R conference. Just got back yesterday. Um, had a great time. There's all kinds of cool stuff being developed in the R universe. A lot of stuff uh, centered around AI because AI and chatbots, LLMs, those are big things. A lot of these different kinds of models are out there. So there's some cool packages. One of them is called Elmer, and it's part of the Tidyverse. And this allows you to chat with um, AI chatbots, all kinds and it hooks up with all kinds of different ones. But you can, OpenAI, Anthropic, all of these different things. You can maybe at the very end of the quarter, um, I'll give you a short tutorial on interacting with this stuff because it's really cool. Um, but I mean, you can start playing around with it. You have to sign up for a developer key, and you might have to put like $5 on like a credit card or something to get like some what do you call it, access tokens and things. But $5 will get you pretty far. But anyway, some cool stuff there. Um, there, one of the kind of funny things uh, that that was brought up is that you know there's AI is good at some things, not so great at other things. One of the things that it's really good at is translation in terms of like, here's some code in this language. Can you translate it into another language? Okay. And and it's true. AI is really good at something like that. Okay, it's much better at that versus saying like, okay, here's a problem and I need you to solve it. Right? Like I've given you nothing. But if you say like, here's code that's working, here's code in R, translate it to Python, or here's code in Python, translate it to R, and and the AI is actually really really good at that. And so, kind of in this time where uh, there's a lot of questions like, why are we learning stuff in R? Like, shouldn't we learn it in Python? Um, because that's what the workforce is asking for and whatnot. There is, honestly, it's kind of like, well, um, we're almost in this like post language world, where you can just say, like, oh, um, I have this almost universal translator in this AI tool that I can just say, well, okay, I know how to think and I know how to execute and I know how to do stuff really well in this language, and it's a matter of just kind of like expressing my idea very clearly in this language, and then having the AI tool to kind of translate it over into another language, and and I think, and it's true, I think that will get you pretty far. Obviously, if you want to learn the other language, you should, spend time and invest in that. But AI is really actually good. I remember, so like I went on a trip to Japan this summer, and you can like ask ChatGPT to like teach you another language, and it can like translate things between English and Japanese and probably every other language out there as well. And it's pretty impressive. So um, yeah, all to say, AI is here. You should be using it. Okay, you should learn how to like learn how to prompt the AI to get what you need. This is going to be an important skill, much in the same way that learning how to use Google and how to like find things that are important to you online, that's an important skill, right? You've probably interacted with members of your family who don't know how to search for things in the internet, and it's like frustrating, and you're like, why are you typing in this? This is not how you find things. And maybe that's some of you also, but definitely interacting with uh, an AI tool, writing good prompts is going to, I think, going to be an important skill. Um, at the same time, of course, you need to learn things yourself, right? All knowledge kind of builds up on each other, and the AI is really good at doing all of this kind of foundational stuff, and then the really kind of advanced and complicated stuff, just because there's not a whole lot out there, it's tough. And so it's important that you learn these things yourself, right? So I don't know, it's it's like, use it, but don't offload all of your thinking. I think there's I don't know if you've seen these other articles about like AI and brain atrophy. Have you heard of this? Where is it? CNN. Okay, well, I don't want to read this. Okay, but just like anything else, if you don't exercise, right, like your muscles atrophy, and if you don't use your brain, if you don't use these kind of critical thinking parts of your brain, those parts also atrophy. So still use your brains. Okay, all right. Anyway, let's take a look at today's topic for the lecture. So we are covering tidy models, okay, which is a system and a tool, I guess a framework that's part of the tidyverse that allows us to create models to fit our data, because our goal is to make good models that will make good predictions. And so the first lines of codes just load up the tidyverse and tidy models. And so here I have that right here. I'm going to just run library tidyverse. Okay, that takes a few seconds to load. Tidyverse and tidy models. Okay. So kind of the philosophy with tidyverse and tidy models is it's actually a lot. It takes not a lot, but like relatively, it's loading quite a bit on your computer, right? Like it's loading all of these packages. It loads a whole bunch of things in your computer, and it's just so that when it comes to you writing code, you have to do less work, okay? If your goal is like, I need maximum efficiency, minimize computing resources, like you're trying to, I don't know, you have like this tiny little computer, like some kind of Arduino or Raspberry Pi system or something that has very limited resources, okay? The tidyverse and tidy models is not the way to go because it uses a ton of memory, it uses a ton of computational resources. But the philosophy behind the tidy models and tidyverse is that the choke point is the human, okay, and so we want to make the human like coding aspect as simple as possible, or give it a unified framework to make that person as efficient as possible, and then don't worry about the computation. I mean, that's kind of like AI, right? Like when you do an AI query, it's using a ton of computational resources, but it's speeding up this kind of human thinking about aspect. Okay, anyway, we're going to start off today looking at how tidy models does linear regression, okay? And I start here. I always start in linear regression because linear regression is something that you guys are already all familiar with 101A. So you're very familiar with the idea of like, here's how we fit a model and here's how we take the results and look at the results of that model. We look at the coefficients, we look at the p-values, we look at the significance, we have all of these things. So this is something that you're very familiar with. And so when I present how it looks in tidy models, which is a little bit different from the standard output, you have a frame of reference. You understand these are the different aspects and these are the outputs of the model. Okay, and then once you understand kind of the framework of tidy models, then when we start introducing other models that you're less familiar with, you have that correct framework in terms of, okay, this is how we specify the model, this is how we get the results of the model and interact with that, and so that's what we're going to do. Now, the flip side of this is because I'm doing everything with linear regression, and you're already familiar with like the basic linear regression tool, which is LM on R, when we do things in tidy models, it's going to feel like, well, this is a lot of extra work. It's going to feel like it's a lot of extra work to specify things in tidy models versus just, hey, when I was doing base R in LM, I just had to write like one line of code. Okay. And again, it's kind of, we want to get familiar with the tidy models framework so that when it does come to using other models, it makes things a lot smoother. Okay, so we're going to start off with just simple linear regression. We'll expand that to multiple linear regression. And as far as linear regression, we're going to just kind of start, I guess, with a conceptual review. Okay, and the data set we're going to be using is this artificial data set for advertising data. Okay, it's an artificial data set, and it's an older data set. And the idea is there a connection between how much money was spent on advertising and how much money was made in sales, right? Like sales revenue. And we always like to think we're immune to advertising, but actually advertising is very, very effective. And so when you spend money on ads, it does increase response rates and stuff. Okay, but again, this is an older data set, and so your variables are dollars spent on TV advertising, dollars spent on radio advertising, and dollars spent on newspaper advertising. But today, like, I don't even know if the newspaper exists as as a physical medium anymore, right? And so probably today a better data set would have like dollars spent on YouTube advertising, dollars spent on TikTok, dollars spent on Instagram, dollars spent on all of these different kind of platforms, and where should your money go? But because everything is online, right? But anyway, this is the older data set. We want to see what's the relationship between dollars spent on these different mediums and the outcome on sales. All right, and so if you just kind of plot dollars spent on TV versus sales, dollars spent on radio versus sales, dollars spent on newspaper versus sales, you see, these are the fake data points that we have. Okay, but still it's useful, and we can fit kind of this. If we fit just one variable at a time, we get these blue lines, and probably TV has the strongest relationship in terms of having the least amount of scatter. Radio has a little bit more scatter. Newspaper has probably the most amount of scatter, but we still see an overall positive relationship, positive slope for each of these things. Okay. And so, when we do linear regression, there's a whole bunch of these questions. What's the relationship between our advertising budget and sales, and how strong is the relationship? How strong is that relationship? Which of these mediums, TV, radio versus newspaper, contribute? How accurately can we predict with each of these things? Is that relationship linear? And another important one is there any kind of interaction or synergy effect where between the advertising media, where perhaps the sum of the two, like if you spend more on TV and more on radio, like somehow together, like you get even more than just adding them. Okay, or do they kind of like counteract each other? Like you're not getting as much, like there's oversaturation and things like that. So those are some of the questions that we want to ask and answer. And so when we do simple linear regression, this is a form that you're very familiar with. You have, your model is your output variable y is the intercept beta 0 plus the slope beta 1 times x plus some error term. Okay. We're going to assume that the error term is normally distributed with a mean of 0, and so that's what you have. And then your fitted values, you just don't include the error term, and it's going to be your estimated intercept, and your estimated slope times x is going to be basically your estimated predicted value for y. Okay, how do we estimate our coefficients? The way we pick them is we said the best fitting model is the one that minimizes the squares. We use the least squares criterion, so we're going to minimize the residual sum of squares. Our residuals are defined as the difference between the actual value and our predicted value. our actual value is y sub I, our predicted value is, beta 0 hat plus beta 1 hat times x sub I. And so we say, okay, this is how we calculate the residuals. We square all of the residuals for all of the observations when we sum them up, okay? And we say, all right, let's minimize that. We use calculus to minimize, and we'll get kind of our coefficients. This is kind of the picture, again, a picture that's familiar to all of us, in that here is the fitted line, the blue line, the actual values are in red, the residuals are the vertical distance between the actual value and our predicted value on the fitted line. And we're going to square all of these things, right? And because, so the blue line is basically our y hat, whenever you have a certain value, like 200, okay, for x, if you plug in 200 for TV, you plug in 200 for x, you're going to just predict one value, but the actual values could be higher or lower than that, right? And so that's why we have the error term to account for the fact that we get different observed values for the same input value, okay? And so when we use calculus and we say, hey, find the slope that minimizes it, okay, we can come up with a formula form, and this is going to work for basically any data set. And we say this is the best fitting slope, the slope that's going to minimize, the intercept that's going to minimize is going to have this formula form. You learn this in 100B and 100C to stats 1, in our class, and we're not going to cover it here, okay? Another way we could think about this is we can create a contour map, okay, a plot of how the residual sum of squares responds to changes in the intercept and changes in the slope, okay? So along the x-axis, I have the different values of the intercept, and along the y-axis, I have different values of the slope. The value is minimized when our intercept is 7.03 and our slope is 0.0475, okay? And that's going to produce the smallest amount of residual sum of squares. If I am off, okay, if I have a intercept that's too high, okay, now my residual sum of squares is going to go up. If I have an a intercept that's too low, my RSS is going to go up, okay? If I have a slope that's too steep, my RSS goes up. If I have a slope that's too shallow, okay, my RSS goes up. And so we have this contour, like this bowl, okay? And the minimum is at the very bottom, where you have a certain value for the intercept and a certain value for the slope. And if you have, kind of different values, your RSS goes up. And, these ellipses kind of show, like, if you have, you can end up getting the same RSS by having a intercept that's too high and a slope that's too low, or an intercept that's too low and a slope that's too steep, okay? So it's kind of like, you can have one that's, I'll show you an illustration later, but, things can be off in different ways and you'll still get like the total same RSS, but the minimum is achieved right here at this red dot here, okay? This is, I guess, a 3D plot of it's kind of hard to see, but it looks kind of like, it looks like a bowl. It looks like, I guess, some oval ellipsoid bowl that, has a bottom there, okay? Here's also kind of an interactive thing where, you have these two knobs, okay? This knob controls the intercept. This knob controls the slope. And so when I turn the knob clockwise, what it does is it slides the intercept, it increases the intercept. And so that has the effect of taking your line and you're increasing the intercept, the line slides up. So if I turn the knob up to the right or clockwise, you can see the intercept go up. If I turn the knob the other way, the intercept goes down. So the line slides up and the line slides down, okay? Meanwhile, over here, I have another knob, and I can turn it, and if I turn it, the line, it changes the slope. So we can make the line, the slope shallow. We can make the slope steeper, okay? So I can change these things. And the goal is for us to minimize the RSS, okay? So, for example, I could choose this as my fitted line, okay? And the fitted line in red is very close. We have these 7 data points. We have a data point in these different colors. And so the line is very close to the orange, the green, the purple, and the pink line. And so we have very small residuals there, but the line is very far away from the blue dot, the red dot, and the brown dot, okay? And therefore, the vertical line is the residual, and then if we square that, so we make the vertical line one edge, this is our squared residual, okay? And so on the right-hand side, this represents the squared residuals, and we can see we have a big squared residual for blue, big squared residual for red, big squared residual for brown. I could say, okay, well, what if I slide that line down? Okay, if I slide the line down, now we're very, very close to blue, red, and brown, okay? And so I have a very small residual for blue, small residual for red, small residual for brown, but now I'm very far away from orange, green, purple, and pink, and so I have these very big squares for those, okay? And our goal is, okay, well, we want to pick overall something that's going to minimize our RSS, all right? So we can try to make our line a little bit, I don't know, something in between. I don't know what the right, it's kind of tricky, but you know, you want to get something where the total of the RSS is as small as possible. And you have these these 2 knobs that you can play with in terms of like one knob's going to adjust the intercept, one knob's going to adjust the slope, okay? And you know, this is the formula that's going to give us the minimum value. But again, this is kind of just like, well, what happens to the RSS if I just turn one of these knobs at a time, okay? And so that's how we fit it. When we get our fitted coefficient estimates, we get an estimated intercept and an estimated slope, okay? And we can say, all right, for the data that we have, this is the slope and this is the intercept that minimizes our sum of squares residuals. And we followed the calculus, we followed the process, this is what we get, okay? However, one issue is that we have to recognize that the data we have is just one possible random sample from the population, okay? And from the population, we could have drawn the same population, we could have drawn different values, and if I drew different values, I would have a slightly different slope and a slightly different intercept, okay? And so the coefficients that we estimate for our data is just one possible set of coefficients. And so we ask this question, if someone else were to observe another data set drawn from the same population, how much would their estimates of the slope and intercept vary, okay? And so we can kind of get at this with a simulation here, right? And so, so this plot on the left, okay, we have the true relationship is given by the red line, okay? So we're simulating our data, and so we're gonna say there's a true relationship between X and Y, and that's this red line. And here I'm gonna just generate random data that's centered around the red line. And so sometimes, you know, we get dots that are above, dots that are below. And so for this particular random set of data, the best fitting line is the blue line. That's the best, that's our estimated thing. And so we say, okay, well, that's what we get. Now, if I did this again and I say, all right, this is the true relationship in red, but I'm going to generate different random data, right? So this is kind of someone else is also trying to, I don't know, we're trying to estimate the relationship between, I don't know, arm span and height. Okay, so I pick some people, I measure their arm spans, I measure their height, and we say, all right, this is the relationship we have, right? You go out to the same population, you measure people's arm spans and heights, you get slightly different data, right? And so your slope and intercept is a little bit different. And if we do that, that's what this plot on the right represents, is you have these light blue lines. Each of these light blue lines represents someone else fitting a different random data set and then fitting the best fitting line there, all right? And so, so as far as this, for this data set, our slope is a little too high, okay? It's a little steeper than what the red line, but the intercept is, lower than the actual value, the red line, okay? We have other ones where the slope is shallow compared to the red line, okay? We have other ones where the slope is too steep. We have ones where the intercept is too high and the ones where the intercept is too low. But overall, all of these different blue lines, they don't seem too far off from what the red line is, okay? And so we have this idea, okay, that on average, the different random lines that we get from different random data sets are centered around the true relationship. And this is what we mean by saying that least squares regression is unbiased, okay? It's unbiased in the long term, meaning that in the long run, if you follow this process, overall, it's going to get the relationship right, okay? In the long run, it's going to get the relationship right. It's going to, in the long run, it'll get the intercept correct. It'll get the slope correct. But again, when you look at your data, it's just one random data set. And so you don't know, am I this blue line that has an intercept that's too low and a slope that's too high? Or am I this blue line that has an intercept too high and a slope that's too low? Or am I this blue line that's off in some other way? Okay, you don't know. Okay, but we're hoping in the long run. I mean, not we're hoping. We know in the long run, it's going to get it right. We're hoping that our particular data set is not like weird and not misleading us. Okay, but you don't know. Okay, and so the least squares regression line is unbiased. Okay. And because we recognize that our intercept and our slope are based on the random data, we also have standard errors. Okay, and we could say, well, if our random data sets, are very different, then my slope and my intercept could be very different from each other, right? Like if I take a random data set, you take a random data set, my slope and your slope could be very, very different from each other. Okay. However, if we're looking at a different data set where there's not a whole lot of variation, okay, like I want to look at the relationship between how many pennies I have and how much they weigh. All right, and you also do something similar. You take a bunch of pennies. Right, so I measure 100 pennies and I measure how much they weigh. I measure 200 pennies and I measure how much they weigh. You do something similar, we're going to get very, very, very similar results. Maybe not exactly the same, okay, because there is a little bit of variation, but we're going to get very, very similar results. And so our standard errors on the slope and the intercept will be much smaller for that data set versus the one for humans, right? And so so that's all taken into account with these formulas, which say, how much does one random slope vary from another random slope? How much does one random intercept vary from another random intercept? Okay, so for the humans, arm span and heights, my slope and your slope could be quite a bit different. For the data set on coins and pennies, and we're looking at how much does my slope vary from your slope, they might vary a little bit, but we're probably going to get something very, very, very close to each other. Okay. All right. And so that's going to be our standard errors. Now, there's a few things. Is that all of these things kind of are built around the assumption that all of our errors are uncorrelated with the variance, okay? And this is not actually true in a lot of data sets, all right? So like if we go back to our television data set, or yeah, right? If we look at this, as my X increases, my variance also increases, right? We see this, it's not constant variance at all locations of X. It seems like as X goes up, my amount of error goes up, okay? So a lot of times these assumptions are violated, okay? However, they are still useful, okay? These models, even though some of their assumptions are invalid, they can still be useful. And so we're going to still kind of go ahead and move forward because they do provide good approximations. But yeah, to assume that the amount of error doesn't change, that is incorrect, okay? One thing I want to kind of point out is when you look at the formula for the standard error for the slope, one is the sum of our errors, okay? So that is as our the number of observations go up, okay, then the entire sum will get bigger, and it's in the denominator. So as the number of observations go up, our standard error will decrease, okay? But another thing is not just the number of observations, but actually how far away our X is from the mean, okay? So if your X values are far away from the mean, you're gonna have a very big value in the denominator and you'll have a small standard error. If your X values are very close to the mean, you'll have a small value in the denominator and your standard error will go up. And that's kind of like estimating, again, think about like our pennies, right? And we want to estimate like what is how much what is the slope, like the weight of the total bowl of pennies, right? Like what's the total weight versus like how many pennies are in there, okay? If you have only a small number of observations, I mean not small number of observations, but like let's say you only have a few values of X, right? You have X is you have a measurement where X is 100 and you have a measurement where X is 101, right? So you have the measurement, like the weight of the bowl with 100 pennies and the weight of the bowl with 101 pennies, okay? And you're trying to estimate what's the slope. And so your estimate of the slope is based on the difference of basically like one additional penny, okay? And so your accuracy will be quite a bit different versus if you measure like how much is the bowl with like 10 pennies versus 100 pennies, okay? And if you say, all right, this is the weight of 10 pennies, this is the weight of 100 pennies, okay? Now the difference, all right, the average would be what, 55? And you have 10 versus 55, you have, your difference is 45. 100 versus 55, your difference is 45. You have a much bigger difference, but you can see like because the difference is going from 10 to 100, now the accuracy of like how much does one penny change the total weight is going to be a lot more accurate, right? So when the X's are a lot more spread out, you can be a lot more kind of confident in your estimate of like how much does one penny change, okay? How much does your slope change for each change in X? So and this is just kind of like just a tiny bit of little random error going up or down. You can see how the slope is going to vary drastically, whereas if your values are more spread out, okay, your slope is not going to vary as drastically there, okay? And so we have standard errors. And so just like we've learned in any kind of statistical inference is we can create confidence intervals, we can perform hypothesis tests. And so with a confidence interval, we can go up or down approximately 2 standard errors. to get like a 95% confidence interval. We can do that for the slope. We could do that for the intercept. When you're looking at a confidence interval, you want to know, like, is my estimate significantly different from 0? And so you're looking to see if 0 ends up inside your confidence interval or not. And if 0 is not inside your confidence interval, you can say, I'm confident that my slope is different from 0, that there is a thing. Okay. Similarly, we could do something with a hypothesis test, and we could, for the slope, we can ask, is the slope equal to 0 versus is the slope different from 0? And this would be a non-directional or a two-sided test. We can do a t-test to see if it is significant. We compare basically the size of our slope versus the standard error on the slope, and then that will lead you to either reject or not reject the null hypothesis. And this all appears when you do LM and you ask for the summary and all of this stuff, right? Okay, so this is the form of the of our analysis that we're familiar with in R, right? So in R, I would do something like read CSV advertising.csv. Okay, so I bring in the data set, all right, and then I would say, all right, let's fit a linear model. Oh, I have to try that. Okay, so I'm going to do a linear model. I want to predict sales based on TV. Is this big enough? Are you guys able to, those in the back? I feel like you guys are so far away. But we have sales, TV, radio. Okay, so I want to fit LM. Oh, the first column is just row names, but we want to predict sales based on TV. Our data comes from our advertising, right? And so what do I call this? Model? Yeah, I'm going to call this model, okay? And so my model shows this. This is my slope, 7.03259. My intercept, I'm sorry, the intercept is 7.03, and my slope is 0.0475. I can call summary on the model. And this is what we see, and we can see, okay, here's our estimate, here's our standard error, this is my test statistic, right? And so we look at something like this. So my slope is 0.0475, my standard error is 0.00269, I have a test statistic of 17. We compare that, so our critical value is probably something around 2. So it's way bigger, right? We're like 17 standard errors away from the mean. And so that's going to be very, very significant. And so we have a p-value of practically 0, okay? Highly significant, 3 stars. And this is kind of how we did our analysis, okay? And then you get your R-squared value of around 0.61, 61 R-squared, okay? And so I think that is familiar to just kind of your how we fit LM. Okay, and so I'm going to show us how to do the same thing using tidy models. Okay, and again, when we use tidy models, in the beginning, it's going to feel very cumbersome because it feels like, oh, I have to do all of this extra work to just kind of get the same results that I have here. Okay, the argument for using tidy models is that sometimes you're going to want to fit a more complicated model, something more complicated than LM. And maybe you've had this experience where you're trying to fit, I don't know, support vector machines or random forest or some kind of regularized linear regression. So you want to fit like the lasso or ridge regression or something like that. And so you call in a different R library, and you have to learn like the syntax for that different library. And there's going to be a whole bunch of different packages there. And all of them have slightly different syntax, slightly different notation for how to do it, and it can become a lot of work, right? You have to read the documentation, and reading the documentation is always a good thing, but sometimes you find yourself ending up spending a lot of time just learning how to interact with this new package, and less time on like fitting the model. Okay, and so what Tidy Models does is it provides this unified framework for this is how I want to specify the model, and then Parsnip, which is part of Tidy Models, is going to translate that to the correct kind of code, okay, for the particular thing. Right now, I guess now in the days of ChatGPT and AI, we could just say like, hey, I want to use this particular package. How do I fit the model? And it's going to do a lot of that kind of work for you. Yes, you can kind of get away with it, but that's still a little bit cumbersome, because when you use a different package, the output of that package is going to come back in a different form. Okay, so if you're familiar with the inner workings of LM, it returns the model as this kind of big list with all kinds of stuff and information in it. And if you use a different package like GLMNet, it returns your information in a different form. And so anyway, we're going to use Tidy Models, and it's going to translate our instructions into the different forms. Okay, so the way we use Tidy Models is we call this this function Tidy Models prefer. What this one does is, as you load up all of these different packages, there's often going to be some functions that all have the same names. Okay, so there might be a function called filter, and there's a filter function in the Tidyverse. There's a filter function in these different packages and stuff. And so when you call the function filter, how does R know which function you want to use? Okay, the default behaviors of R is it's going to use whichever package you loaded last is going to be the version of filter that it's going to use. Okay, Tidy Models prefer says, you know what, don't worry about the order in which I loaded these packages. Just if whenever I use a function name and you see this function, the same name exists in other places, always use the one from the Tidy Models and the Tidyverse. Okay, it's kind of just like if you have multiple people and 2 people have the same name of Joseph. Which Joseph am I talking about? I'm always talking about the one in my stats class. Okay, don't worry about the ones in other classes or things like that. That's basically what Tidy Models prefer is stating here. Okay, it just says if there's a conflict with different names, just prefer the Tidy Models ones. Okay, and so this kind of goes through and it says, all right, where do we have conflicts? Okay, we're gonna specify the linear regression model. Okay, this doesn't actually fit a model. This just creates a model specification object. Okay, and this just says here we're going to build a model, and we're just going to say, all right, what kind of model do you want? We want a linear regression model. And how are you going to estimate your coefficients? Okay, with linear regression, we are going to estimate our coefficients using the engine LM. All right, and this is just kind of the basic linear regression model. So let me just take us to Parsnip. And under the reference, there's all of these different models that we can fit. Okay, so under the Parsnip package index, so Parsnip again is our translation system that says, you want to fit all of these different models. These are the different models we can fit. And when we want to fit like a linear regression model, we can use all of these different packages. And you go, well, how many linear regression model packages do you need? Okay, well, we have LM, all right, that's the one that we're familiar with, but there's actually a whole bunch of other kind of packages. So there's Brule, which uses neural networks, PyTorch, okay? And so, I don't know, like in French, Brule is like when you burn the burn the sugar on your cream, right? Anyway, so using a torch, okay? But then there's like GLM, which maybe you used for like logistic regression, and then there's GLMNet, and then there's, I don't know, all of these different things. Stan uses like Bayesian stuff, and you can fit kind of these different, I guess, variants of linear regression. So there's like regularized linear regression with lasso and things like that. It's just a form of LM. So anyway, you can fit a linear regression model, and you can use any of these packages, okay? And when you do this, you say, I want to specify this particular engine. So that's what we're going to do. We're going to create a linear regression model, okay? And so this is just kind of a placeholder, and I'm going to set the engine like this. Okay, so I'm going to just kind of copy and paste this into R here. So I'm going to create a linear regression model object. Say I want to create linear regression, set the engine to LM. Okay, so all this is just a model specification object. And if I ask, hey, what is this? All right, what is this LM model that this object that I just said? It's just a model specification. It doesn't actually have any, I haven't associated it with any of the data. I haven't gotten any results, okay? So now what we do is we want to take that model specification and we want to fit it to the data, okay? So we're going to say, all right, here is this thing. You're going to fit it to this particular data. And so this part, we fit almost like an LM call, okay? And so we're going to say, all right, take LM model, and we're going to fit it to, oh, by the way, there are two forms of the pipe, and I just haven't updated my notes. So the latest version of the pipe, do I need to explain the pipe? You guys has anyone not familiar with the pipe? Everybody's familiar with the pipe. Okay, so are you familiar with both forms of the pipe also? Okay, all right, great. Then I don't have to explain. But this is the base pipe. This is the kind of the preferred form now. This is the Magrider pipe. I just haven't updated my notes to all use base pipe. Okay, so anyway, we call this fit. You know, much like we want to call LM sales as predicted by TV. Our data comes from the advertising data set, and then we should probably store this somewhere. And so I'm going to store this in an object called LM form fit for linear model formula fit. Okay, and then that just fits the data. And so I can say, all right, what is LM form fit? And now we have a parsnip model object where it has been fit to the data. Okay, and it can say, all right, and now we see, oh yeah, here's my intercept and here's my slope, and it looks a lot like LM. Okay, so that's what we have there. There's other forms of calling fitting a model. Another one is fit XY. Okay, and so depending on your data, you might want to fit to I guess matrix form. And so if you've ever used Python and scikit-learn, all of the calls in scikit-learn are in XY form, meaning you have to have a separate kind of vector or matrix for your predicted variable, and then you have a vector or matrix of your, what did I say? You have a vector matrix for your response variable, you have a vector matrix, you have a vector for your response variable, you have a matrix of your input variables, your predictor variables, your X, and then you fit the response to your inputs. And so here, I would kind of create like an X matrix. And so I would just kind of take my advertising data, and I would select for my X matrix, I would select the column TV. Okay. And then for my Y, I would take the advertising data and I would select the sales column. Okay. And so I have basically just the column, this matrix or data frame, the column of X, column for Y. That's what we have here. And then I can also just take the model specification, right? And I can call fit XY. And I'm going to say X is this X column that I created, and Y is going to be the Y column that I created. And that's that. And I would say, I guess this, what did I call it in the notes? LM XY fit. And we'll do that, okay? So we just call fit XY. X is X, Y is Y. This is, now I have these objects here, and I can say, what is my LM XY fit? And we have the same exact results. Okay, so these are just different ways to fit our linear model, our model specification, to our data. Okay, and so depending on how your data comes in, you might use the formula fit, which I guess you're accustomed to now in R, or you might use the XY fit, which I will say the formula fit, if you did not grow up on R, like if R was not your first thing, this is like the weirdest thing to see, okay? Like if you're coming from like Python or the CS world and you see kind of this formula fit, it feels very strange, okay? Whereas this is going to be feel more familiar to you. Whereas for those of you who are kind of like first exposed to R and then Python, then this might feel a little bit stranger. But basically, it's just it adapts it to kind of both of these things. All right. So anyway, we have the same kind of thing, and we have that. Okay. Whatever you have, you can inspect the output of this. Okay. And so there is this argument, or not this argument, this function called extract fit engine, which I demonstrate here to just show you that what Parsnip does is all it's doing is it's just translating your request into the request for the native thing, which in our case is LM, okay? And you can get back the actual output of that LM, which is this extract fit engine thing, okay? So here, LM formula fit is what Parsnip created, right? So if I do this is a Parsnip model object, whereas with extract fit engine, it looks almost exactly the same, but this is the result of just kind of calling it with exactly LM. So if I ask, you know, what is this? It's a class LM, okay? Versus what is the LM formula fit? This is it says underscore LM. This is a model fit is basically the Parsnip thing, okay? So here the extract fit engine is going to be exactly the same as this model object that we created back in LM. So like if I extract fit engine, let me just call this model 2, and I can do all equal model and model 2. Oh no, it doesn't like that. Okay, but so model 2 looks like this, and model, these are basically the same kind of same objects here. All right, it's the same. It's the same result. Okay, so you can extract out from the Parsnip object the actual thing. Okay, that are produced. Okay, but this is not how we want to kind of interact with it, right? So I can extract fit engine, and with LM you can call summary on it and all kinds of stuff. But I would say this is not what we generally do. Okay, instead, tidy models, we want to kind of take the results of the fitted object, and if we want to inspect the results, we throw in a function called tidy. Okay, and what this does, So here's my LM formula fit. This is my parsnip model object. I'm going to throw it into a function called tidy. Okay, and what this does is it's going to return a table of basically the estimated coefficients. Okay, what parsnip does is it says, okay, what are the kind of the important things that we need to know about this model? And as far as a simple linear regression model, we just need to know really our intercept and our slope. And so what it does is it extracts all of that information out and outputs the result into a tibble, okay? Into a tibble or a table that we can actually use, right? So I can take this, and if I want to get the column of standard errors, okay, I can call select, and I can say I want the standard error column, okay? And we get those values, okay? If I want to get the p-values, I can get the p-value column, okay? And we can get those actual values. Versus with LM, okay, I have my model here, and I can call summary on the model, okay? But how do you get this? How do you get this test standard error, right? Or how do you get the p-value? How do you get these p-values? It's not so easy to get directly, right? Like if you wanted to use this value later, okay? What just happened? Okay. So it's actually not so easy to get these values out from plain old LM, whereas using calling tidy on it produces a tibble that we can interact with. Okay, and so so with that we can do this. You can also get more of the summary values as far as like the R squared and all of those kinds of things, the AIC, the BIC, which is all kind of in here as well. You can get all of those things out with the function glance. You glance at your formula fit, you call glance on it, and this will give you all of those values that we see that we normally get when we call like summary on the model, right? So your multiple R squared value of 0.6119, we have it right here, 0.612. I mean, you can, if I call glance and I say select R squared, and if you want to just when you call select, it always returns as a tibble, okay? And if you want just the vector, you call pull, all right? And you get the actual vector form, not in a tibble, okay? So you can get all of these values out and interact with them as well, right? And so you can get the AIC, the BIC, any of these values here that could be useful as well, okay? And so tidy models just makes it a lot easier to kind of get these values and extract them versus just it's the difference between like someone taking a picture of a table, right, versus like sending you the table itself. And so like, because if somebody sends you a picture of the table, like you have that information, but then like later on you like want to copy and paste the numbers out of that thing, it's like it's frustrating when you're dealing with a photo of it, right? And similarly, when you call summary on the model, you have that information, but then like if you want to get this information and use it later, like how do you reference this? And it's like frustrating. So by using tidy and glance, like these are all values in a table and you can pull them out for interaction, okay? So you're not getting anything new per se, but it's in a form that's easier to interact with, okay? It's much easier to work with a table that somebody sends you versus a screenshot of something, okay? And that's kind of what we have, okay? Okay, so yeah, again, here if you want to extract out any of the values, you call glance to get it in this table form, and then you select the column that you want, and then to get it, because select always returns a tibble, which can be frustrating to work with, you call pull, and pull will take the column and return it as a vector, okay? Which might be the form that you want to work with, okay? So we're all, I just want to kind of make sure we're all okay with the tidyverse and the select and the pull and all of that stuff. Okay. All right. So then if you want to call predict, okay, you can call predict on this. So if you want to make predictions, you create a new data frame with the column named, right? So here, if I want to make predictions for values like 200, 150, 100, okay, I can create like a test data set, okay? So I'm going to just create a data frame called test TV, and I'll call this Tibble. The column name is going to be TV, and what, I forgot what my values do I have? 200, 150, 100. Okay, I guess Tibble or data frame doesn't matter. So here's test TV, and then I'm going to just feed this into my fitted value, right? Or fitted model. So I have LM formula fit, and we're going to call predict, and we're going to give it the data frame of our test values, okay? And it says, okay, these are our predictions. We would, for 200, we would predict 16.5, 14.2, 11.8, okay? So these are my prediction values, and that's what we have. So we predict on our new data right here, just like that, okay? You can get kind of all of your predicted values by just throwing back the entire data set in there as well, okay? So you can do all of advertising. You can also ask for like prediction intervals, okay? So prediction intervals kind of take into account your standard errors and whatnot. So here I can say predict on the entire advertising data set, and we have everything here. And we can also ask as far as the type of predictions, not just the mean value, but I can also get the upper and lower bounds, okay? So I can say type is equal to prediction interval, okay? So these are your lower and upper bounds for your prediction intervals, okay? So all kinds of things that you can do. And so as we have this, you can take all of these things and you can bind all of these columns. So we can have the actual value of sales, the input value TV. We can say, where is my prediction interval? Okay, my prediction is 17.97. My lower bound and my upper bound, what is all of this, right? And so all of these things, you know, how do you get this output? We just kind of build up, right? So every time you see a pipe, you just kind of say do and then, right? So take the advertising data and then select the column sales and TV, and then bind a new column. What is the new column of values that I'm going to bind? Okay, well, take the predictions from the formula when you make the predictions on advertising, okay? And then bind additional columns. Bind columns where you do the prediction interval. So you get your lower bound and your upper bound. Okay, so I'll go ahead and I'll just kind of copy and paste this into R, and I'll run this here. Okay, and so here we go. We get our prediction, our lower and our upper bound. And then, you know, once you have this, you can do further things, right? You can say, you can ask, all right, how many times was the actual value outside of my prediction interval, right? So you can bind a further column, or I guess you can mutate, and you can ask, is sales, is it, oh shoot, I want to say, there's a function called inside. No. Is it between? Let's see. All right. So let's say I want to just see if sales. So we're going to mutate. We want to create a new column, and I'll call this inside interval. And this is going to be, we're going to ask if sales is greater than the dot prediction lower, and sales is less than dot prediction upper. Oh, I hope this is right. I haven't actually done this. Okay, so we get true, 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 true. Is that right? It looks okay. Print n equals 200. Do we have it? So we have a false here. 11.8 is below the lower. Okay, and we can kind of ask, how often is our prediction correct? All right, so we can select this column of inside the interval. So we have that. Let's pull it. And so I have this vector, and then let's get the proportion. And so I'm going to call mean, and it's inside 95.5% of the time, which is about as good as we can hope for. Okay, so if we're making a 95% prediction interval, the idea is basically I feel 95% confident that the actual value is going to be between the lower and upper bound of my prediction interval. And when I calculated it, it was, for a random data set, it was inside our interval 95.5% of the time, which it's like, oh, that's pretty good. Okay. And again, it's just all in the form of doing this, which I think if you were not equipped with tidy models and I said do this, it's kind of a pain. It's kind of a pain to do manually, and tidy models makes it a lot easier. And I hope we feel okay about this. All right. So we can make predictions. We can use it to make prediction intervals and whatnot. Okay. All right. A few other things. All right. So we can talk about the residual standard error. This is kind of like what's your typical amount that the response deviates from the true regression line. Okay. And then you can get values like your R squared value, which is going to be, you have your total sum of squares TSS, and you have your residual sum of squares, basically what's left over, what cannot be explained. And so your R squared is basically 1 minus what can't be explained. This is like the proportion that can't be explained, and therefore your R squared is kind of like the proportion that can be explained by the model. And so here is just a very, very silly example. Okay, I'm going to create just a very tiny little data set. X is the values 1, 2, 3, 4. Y is the values 2, 6, 4, and 8. The correlation between these two variables, X and Y, is 0.8. And so our R squared is going to be 64%. We say, all right, predict Y based on X. We get an intercept of 1.0, a slope of 1.6. And this is kind of our picture here. All right. And so these are the observations: 1, 2, 2, 6, 3, 4, 4, 8. This blue line represents Y bar. If you had no predictor variable, what you would predict is just the mean of all the Y values. So if our values are 2, 6, 4, and 8, the mean of the Y values is 5. And so if you're not going to use X as a predictor, you would just predict 5 for everything. So this forms our baseline. Okay, the total sum of squares is how different is our value from our observed value from our predicted from the baseline, which is Y bar. So the total sum of squares is basically the sum of the green lines, basically how different is each value from Y bar. So this is 4, our actual value is 2, so this is 3 away, 3 squared. This is 1 away, so 1 squared, and 3 squared. So our total sum of squares would be 9 plus 1 plus 1 plus 9. This the green lines squared, so 20. Okay, whereas our RSS is what is the orange lines, which is basically the residuals after we fit the line. So when we fit the line, The best fitting line is this red line with an intercept of 1 and a slope of 1.6. And so the prediction here is 2.6. The actual value is 2. So our RSS is going to be 0.6. I'm sorry, our residual is 0.6, and 0.6 squared is 0.36. For this next value, we predicted 4.2. The actual value is 6, so our difference is 1.8. 1.8 squared is 3.24. This is also, the orange line here is 1.8. The orange line here is 0.6. And so when we square those up, we get 0.36, 3.24, 3.24, and 0.36. And so that adds up to 7.2. And so therefore, the amount that is unexplained, okay, is 7.2 out of a total of 20. The amount that is explained would be 20 minus 7.2, so what's that, 12.8? 12.8 divided by 20 is 0.64, and that's how we get our R-squared value, is we're saying we're able to, this model is able to explain around 64% of the variation, right? So this is, I think this is all review from 101A in terms of the definition of R-squared here, okay? Okay, we can expand this from simple linear regression to multiple linear regression, where we just do it now for more than one predictor variable, okay? And so rather than just having an x1, now we have x2, x3, up to some arbitrary number of variables p, okay? And we just have a beta coefficient. And again, because it's linear regression, we're just multiplying each of these predictor variables by beta. Now, it is possible that, say, this x2 variable is just the x1 variable squared or something like that, right? It could be a transformation of one of these other variables. But once you create that variable x2, which is like maybe the square of the x1 variable or something, now you just treat that as its own thing, okay? We don't necessarily say there's a link, okay? So we just kind of include those, and we estimate our coefficients, and so on and so forth. And we kind of just do, using the same rule, minimize the RSS, and at this point, it's now like, if you have two variables, an x1 and x2, linear regression is basically fitting a plane to your data, okay? And so the picture here is, rather than just a straight line, and you have residuals, which is how much your dot differs from the straight line, now we have this plane, okay, or in higher dimensions you have a hyperplane, and you still have vertical residuals. You have the difference between what you predicted and what the actual value is, and we're just trying to minimize the RSS, the residual sum of squares, for this thing, okay? And so we can do this for our advertising data. We have different predictor variables. We have dollars spent on TV ads, radio ads, newspaper ads. Our response variable for all of these things is sales, okay? And so we'll fit simple linear regression between each predictor and the response variable. And here I'm going to do this using tidy models. And so I'm going to say we're going to do LM for TV, LM for radio, LM for news, okay? And for all of these things, just for funsies, I did LM news by extracting out X and Y. But I mean, I could have just copied and pasted all of these things. All right, so we're going to fit our three models here. And here I'll just do fit sales as predicted by newspaper. Wait, is it newspaper? Yep. Data is advertising. Okay, so I have my three models, LM TV fit, oops, LM radio fit, and LM newspaper fit. Okay, so we have all of these things, and we want to, let's say we want to interact with these things. I can just call tidy, and we'll get out all of these terms. Okay. And when we look at all of these things individually, okay, we can see all of them have p-values less than 5%. All of them have p-values that are really small, right? So our TV has a p-value of 10 to the negative 42. Here we have 10 to the negative 19. And newspaper, it's the least, I mean, our p-value is the biggest, but it's still 10 to the negative 3. We still have a significant p-value there, okay? However, if we combine all of them, okay, and I say, all right, predict sales based on TV, radio, and newspaper, and so we're still doing kind of our formula fit with using the plus sign here, and I say tidy these up, now our p-value here is 8.6 times 10 to the minus 1, so that's a p-value of 0.86, okay? And so we see this is not significant, okay? And so this is just kind of the combined fit. Okay, and so I could pull out I can select the p-value. Okay, and you can see this this last values is quite big, 0.859, 10 to the minus 1, so 0.86 basically, right? So big value. That is not significantly different from 0. And, this is review for you. You already know this. How can it be significant over here, but not significant, right? In the individual model, how can newspaper be significant, but then in the combined model, it no longer be significant? And that's because we have collinearity, right? In that, if you look at the correlation, there's positive correlation between all of these variables, right? So when we spend more on TV, we also spend more on radio, and we also spend more on newspaper and things like that, right? So there's correlation between radio and newspaper. It's not super high, okay, but it is positive, right? And so that means in a place where you have high newspaper advertising, you also tend to have higher radio advertising, okay? And so the true relationship, okay, is that sales is associated with, say, radio advertising, but not necessarily associated with newspaper advertising. But because in markets where newspaper advertising is high, is also where radio advertising is high, if you're only looking at the relationship between newspaper and sales, it's going to look like, oh, well, we spent a lot of money on newspaper and our sales are higher, right? When we didn't spend a lot of money on newspaper, our sales were lower. But it's really, the true relationship is when we spend a lot of money on newspaper, we also spend a lot of money on radio and sales are higher. And it's really the radio that's responsible for the change, okay? This is not news to you. You understand how this works, but this is just kind of reflected and brought up again, okay? So, when we do something like this, okay, and we want to kind of fit similar models multiple times, right? So here, I basically did all of this stuff, right? I want to fit the model to TV, the model to the radio, the model to newspaper. We can create, instead of having to kind of specify different models and fitting them every single time, okay, we can create a model workflow, right? And so for this example, it's a little overkill, okay, because it's simple enough where we don't have to do it, okay? But we're going to kind of just establish some of the framework now, so that later on, when we actually do want to do complicated stuff, we have a workflow and we have a system in which we can do this, okay? So we're going to create what's called a workflow. All right, so here I establish my linear model parsnip model specification. Okay, so this is the exact same thing that we had before. We're going to specify, I want to fit linear regression using the engine LM. Okay, so this is exactly the same as before. And now I'm going to create a workflow object, okay, which is done by this command workflow. Okay, and as far as this workflow goes, we're going to just create a very basic workflow. We're going to add a model to it. Okay, so when you set up a workflow, it'll be something like adding a model and adding a recipe. Okay, usually is kind of the two elements to a workflow. A recipe is basically how you interact with, like, what variables you want to use, and do you want to clean up any of your variables. And then the model is going to be, what model you want to fit. And so a workflow will consist of these kind of two parts. Basically the recipe, which is which variables are you selecting, along with, do you want to transform any of your variables? Like, do you want to take the log of any of these variables? Do you want to throw away outliers in any of your variables? Do you want to do any kind of I guess feature engineering is also part of that recipe step. Okay, and then once you have that recipe, you pair it with a model. Okay, and the workflow allows you to kind of mix and match these different aspects. Okay, where you can say, all right, I want to try this model with this variable selection. I want to try the same model with a different variable selection. I want to try this model with a different variable selection. Okay, and then later on you want to say, hey, I want to try a different model. Right? I want to, instead of linear model, I want to fit random forest, and I want to do random forest with this variable selection, random forest with this variable selection, random forest with this variable selection. Okay, right now it's overkill because we just have the linear model. I don't have a ton of different variable selection options, but let's just kind of start establishing this. Okay, so we start off our workflow with just adding our linear model to it. Okay, and then here I'm going to create basically the list of, here I've got a formula list. This is going to be the list of all of the kind of different variable selection things I want to do, right? So here I want to have one model where I'm going to fit predict sales based on TV. I want another model where I'm going to predict sales based on radio. I'm going to predict another model, sales based on newspaper, and then I'm going to have it sales predicted by TV, radio, newspaper, sales predicted by TV and radio, sales predicted by TV, newspaper, sales predicted by radio, newspaper. So this is just as far as the different models I want to try out. I just have these different kind of variable selections. Okay, and again, this workflow framework is very powerful and extends beyond just variable selection. But here we're going to just start off with variable selection because this is something simple that we can kind of explore and understand. So here I'm just creating a list of a whole bunch of different formulas showing the different variable selections. Okay, and then now I want to fit the model, all of those different kind of, I only have the linear model, okay? But again, I can create like a whole bunch of different things. So I create a workflow set by taking my pre-processing the recipe or the list of formulas along with the different kind of models I want to fit. So in this case, it's just the linear model, but if later on we can do, I want the linear model, I want the regression, random forest model, I want this model and that model, okay? So these are going to be the different models that I'm going to fit. This is going to be, we're going to call this the workflow set, okay? So I'm going to run this, okay? And so if I ask, what is this thing? It's, when I say, what is this thing that I just made? It's going to say, you just created a workflow set, okay? And again, in the tidyverse, every object you create is a tibble. And so it comes back basically in this rectangle form, but it's like, it's weird, okay? Because basically my first row is this, is the TV. So you'll see the names here are basically the name of the different formula objects. Okay, so the first formula was called TV, the next formula was called radio. Okay, and then as far as when I created my workflow set, it was I just said the LM. Okay, so then it just kind of puts an underscore and says, okay, you got TV underscore LM, radio underscore LM, news underscore LM. If later on I have a different thing like random forest and I call it RF, okay, RF is going to be my random forest thing, then we'll also have TV underscore RF, radio underscore RF, and things like that. So it just kind of combines all of these things. And then we can say, all right, what is this, this first, let's look at this first column, and it says it's a tibble, and can extract that out, okay? And we can see, all right, this whole thing, this is a, it contains the information, and it says the model that we want is linear regression, which is that object. And it says the pre-processing is a formula, so we can also extract out what that is. All right, it says it's a formula and so on and so forth. Basically, it has all of the information inside each of these things. We can ask, what is this workflow itself? Okay, and it has the information, and it says, okay, your preprocessor, these are the variables that you're selecting. This is the engine that you're running. Okay, so all of the information is stored inside a tibble that we can extract out if we ever want to get stuff. So I guess this is something you have to kind of get used to, is none of your information is lost. It's always going to be in there, but how do you get it out? And you just, it's always in the form of a tibble here, okay? So anyway, you can ask, all right, what is that workflow information, and so on and so forth, okay? So we have this workflow set. We can then fit all of these things, okay? So I have all of my advertising models. Okay, we have all of them, and then we can say, all right, let's fit it to our data, okay? And let's evaluate it, right? And so I'm going to just kind of skip a whole lot of stuff, and this is just to show you, like, all right, this is where we can go, and don't worry, in the coming lectures I will explain exactly how we get up and set this up. But let's say we want to do cross-validation, so we can get a sense of how well all of these different models perform. Okay, so I'm going to create tenfold cross-validation here I'm going to call vfold CV on my advertising data. Okay, so I have these are all of my different folds here. Okay, and then we're going to try out all of these different models. We're going to fit all of the models onto these things. Okay, and so this is the function. It's called workflow map. Okay, and this is basically going to say you have all of these models set up. Okay, we've got 7 of these different models to run, and I want you to fit it on the data, and I want you to not just fit, but I want you to do cross-validation and measure its performance on each of these different things. Okay, and so oops, so that's done here. Take all of the different models you've specified. Okay, workflow map says map this instruction. Okay, the instruction is fit the resamples. Okay, map that instruction onto all of the different folds, onto all of the different models you have. And when you do fit resamples, you need to say, all right, how are you going to measure the performance on what data, what folded data set you want? So we're going to take our advertising folded. Okay, so here it's running tenfold cross-validation on all 7 different models, and you can see it took a few seconds to do. Okay, and we can see, all right, how did this perform? All right, and so this is the results. It has all of the results stored in here under results here, and we can take a look at this by calling collect metrics. Okay, collect metrics gives me all of the kind of metric performance, RMSE, R squared values, and things like that. And so let's take a look at just the root mean squared error. Okay. All right. So here it's we can kind of compare all of our different models and see which one has like the best performance. And so we want the model with the smallest root mean squared error, which if I arrange in descending order by mean, which one do you think is going to have the smallest? Well, I guess you can see it, but the one that has the smallest root mean squared error is the one that just has TV and radio. Okay, the second smallest is the one that includes all of them. Okay, which makes sense. Okay, so the worst performing model is the one that uses only newspaper. Okay, the second worst is the one that uses radio and newspaper. Okay, and then here the next is radio. TV does better. TV and newspaper does better than TV alone. Okay, so you have to think like newspaper by itself is not related to anything. Okay, is not actually related, but newspaper is correlated highly with some of these things. So by seeing newspaper, you get a sense of radio, right? And so the best performing model, the real relationship is between the sales numbers and TV and radio. Okay, but if you don't have the radio numbers, newspaper contains some of that signal for the radio numbers. Okay, but if you have the radio numbers, the newspaper is just noise. Okay, and so that's kind of reflected here, where the best performing model is the one that only takes into account TV and radio. If you add the newspaper and you have all three of them, you're just kind of including noise, and so your mean squared error is actually a little bit higher. Okay, if you don't have the radio, then the next best thing you can do is TV and newspaper, where newspaper contains some of the signal of radio. Okay, and if you don't have that, then TV is fine, and if you don't have that, then radio by itself is fine. You know, radio along with newspaper maybe is going to perform a little bit better than just newspaper all by itself. Okay, but anyway, this is all kind of reflected as far as using cross-validation to evaluate our performance. Okay, and I don't know, you may or may not be impressed, but doing this kind of work and fitting all of these different models and all of these different data sets and all sorts of stuff all at the same time, without tidy models, this would have taken a long time. Okay, this would have taken a really long time to do. And tidy models just makes this nice and easy, and it allows you kind of take a peek at all of these things. Okay, so we will discuss all of this and expand, get into the details on all of that. I hope your homework's coming along okay. If you know, some of you I think just added the course, and if you need an extension for the homework, come talk to me. I'm happy to grant you an extension. And even if whatever, you know, I'm pretty flexible with deadlines and stuff. So I just want to make sure everybody does their stuff, but I am flexible with deadlines. So anyway, we'll wrap things up for here for today. We'll come back on Thursday and take a look at more tidy model stuff and start getting into looking at these different data sets. Okay, all right, we'll see you then.